Hello everyone, this is my 17th video on infinite series. In this video we shall consider one more example on testing the given series for convergence, absolute convergence and conditional convergence. So let us consider the first problem. The problem is given here, the question. So the alternating series is like this and we have to check convergence, absolute convergence and the conditional convergence of this series. Now let us first write down the given alternating series in the standard format. So here summation minus 1 to the power n minus 1 into un, this is the standard format of an alternating series. So it is given as summation minus 1 to the power n minus 1 into 1 divided by 2n minus 1 whole to the power of 3. The given expression I have written as it is. So this implies that un here is 1 divided by, this is un. This is same here in both of the two cases. Here this is un on LHS. So on RHS it is 1 divided by 2n minus 1 whole to the power of 3. So this is very simple task we are having here to determine un. So after determining un, we will move on to the first question, that is to test the convergence. So to check the nature of the given alternating series for convergence, we have to apply the Leibniz test that we have discussed in our previous video, one of the previous videos. So to apply the Leibniz test, we should have what is un plus 1. So from this un we are having in hand, let us now find out what is un plus 1. So un plus 1 is 1 divided by 2. In place of n we have to write n plus 1 in un. So that gives us un plus 1. So it is n plus 1 as it is minus 1 whole to the power of 3 as it is. Now it is 2n plus 2 minus 1. So it is going to be 1 divided by 2n plus 1. It is 2n plus 1 whole to the power of 3. After having un plus 1 and un in hand, we shall check the first condition of Leibniz test. That is, we want to show that un is greater than un plus 1. For that, we observe here that 2n minus 1 is always less than 2n plus 1. This is a very trivial thing for every n. That is 2n minus 1 is less than 2n plus 1. This is for example, when we put n equal to 1, we get 1 here, and this is less than 2 into 1 plus 1, that is 3. So 1 is less than 3. This is very trivial for every n. So 2n minus 1 is less than 2n plus 1. This thing we know, and that implies 2n minus 1 whole cube is less than 2n plus 1 whole cube. This is also very easy for every n. We can directly say like this, that is rising both sides by the power 3 will not change the inequality, same, it remains same. Now when we take the reciprocal, that is when we take the reciprocal on both sides, that is 1 divided by 2n minus 1 whole cube, and here also 1 divided by 2n plus 1 whole cube. Why we are taking the reciprocal? Because we are having the nth term as 1 divided by 2n minus 1 and n plus 1th term as 1 divided by 2n plus 1 whole cube. For that reason we are taking the reciprocal of these. So when we take the reciprocal, the inequality reverses, less than becomes greater than for every n. So from this, what is this? This is un, and what is this? This is un plus 1. So we have proved the first condition, that is the first condition of Leibniz test is verified. Now let us consider limit of n tending towards infinity of 1 divided by we should write un here, limit as n tending towards infinity of un, that is equal to limit as n tending towards infinity of 1 divided by 2n minus 1 whole cube. So when we directly put infinity here, so it is 1 divided by infinity, that is of course 0. 1 divided by infinity, that is going to be 0. So limit of n tending towards infinity, what we have proved, that is limit of un as n tending towards infinity is equal to 0. This is the second condition of Leibniz test. Both the conditions are satisfied. Therefore, From 192 we can conclude it implies given alternating series is convergent as per the Leibniz test. So the first part of the solution is over. So let us move on to the second part, absolute convergence. So for the absolute convergence, we should write, in order to check the given series for absolute convergence, we have to write down the absolute series. We have to write down the absolute series. What is absolute series? Absolute series is the series obtained from the given series simply by making all the terms positive. So the absolute series is summation of un. We have to ignore minus sign. So summation of un. What is summation of un here is 1 divided by 2n minus 1 whole cube. So this is the absolute series. From this, what is un? Un is 1 divided by 2n minus 1 whole to the power 3. Now let us simplify this. So this is equal to 1 divided by, one can take n outside. When we take n outside, it comes along with its power, that is 3. And in the bracket, it is 2 by n remains. We are taking n outside. When we take n outside, it is 2 by n remaining. Sorry, actually 2n by n cancelled, and it will become 2 minus, here it remains 1 by n. So when we take, and the power is as it is, when we take n outside from this, we get this type of thing. That is, after taking n outside, it becomes n cube outside. Within the bracket, it is 2n by n. Of course, it is going to be 2, because when we take n outside, it remains only 2 minus 1 by n. So that is equal to, we can take this 1 by n cube separately here, and the remaining thing 1 divided by 2 minus 1 by n. And let us say, let us take Vn equal to 1 by n cube. Let us take Vn equal to 1 by n cube. So therefore, we get Un equal to, here, Un equal to 1 by n cube. In place of 1 by n cube, we shall write Vn into 1 divided by 2 minus 1 by n. Now this Vn we can transfer to left hand side. So as to get Un divided by Vn equals to 1 divided by 2 minus 1 by n. Now let us take limit. So here we should understand that we are going to use the comparison test. So therefore we are supposed to take limit on both sides. So when we take limit as n tending towards infinity of Un divided by Vn, we are going to get limit as n tending towards infinity of 1 divided by 2 minus 1 by n. So it is 1 by 2 as it is minus 1 by infinity. We have to substitute infinity here. So 1 by infinity is going to be 0. So this is 1 by 2. So we get this limit as a non-zero finite quantity. So when we get a non-zero finite quantity, therefore by comparison test, it implies summation Un and summation Vn behave alike. This is our conclusion from the so-called comparison test of type 3. Since summation Vn, what type of series it is? It is summation of 1 by n cube, because we have taken Vn equal to 1 by n cube. So Vn is summation 1 by n cube is a p series, or an harmonic series, we also call it as, it is a harmonic series. So it is a p series with p equal to 3 and it is a number greater than 1. When p is greater than 1 in the p series, it implies that summation Vn is convergent. When summation Vn is convergent, it implies summation Un is also convergent. So what we have proved, that is the absolute series is convergent. The absolute series of the given alternating series is convergent. When the absolute series is convergent, it implies the given alternating series is the given alternating series is absolutely convergent. So we have proved that it is absolutely convergent. Now, when it is absolutely convergent, there is no question of having the conditional convergent. Therefore, the given series is convergent and it is absolutely convergent. And third question, that is conditional convergent, we can directly conclude that it is not conditionally convergent. So this completes the solution of the problem. Thank you.